Okay, this will be the last chapter, and it'll be two lectures. Tonight lecture, and there will be another lecture, and then we will finish the material. The chemistry of saline and sodic soils. This material is all in your textbook. There is a chapter in your textbook, so everything in these lectures will be from your textbook. Salinity can be defined as the concentration of dissolved mineral salts present in waters and soils on a unit volume or weight basis. So there are two different ways of expressing salinity. We will talk about them as we go, based either on volume basis or weight basis. Salt-affected soils can be classified as saline, sodic, saline, sodic. So we have three different types of salt-affected soils, soils that have salinity problem. They have salt problem. So they can be either saline, sodic, or saline, sodic. Saline soils are plagued by high levels of soluble salts. Plague, that means they have a problem. Their problem is high levels of soluble salts. Sodic soils have a high level of exchangeable sodium. That's from the name, sodic, sodium. Sodic problem of sodium. Saline, sodic, they have the two problems together. They have salinity and they have sodium problem. They have both high contents of soluble salts and exchangeable sodium. Salt-affected soils occur most often in arid and semi-arid climates. We don't find this type of soils in the tropics or semi-tropics. They will exist only in areas where you don't have enough rainfall to wash down the soils through the profile. Why do we get salinity? The causes of soil salinity. Sorry. Soluble salts in arid and semi-arid climates. There is not enough water to leach soluble salts from the soil, what I just said a minute ago. So you do not have enough rainfall to keep leaching these salts out of the soil profile, so they accumulate in the soil. What are the major cations? Sodium, calcium, magnesium, and potassium, the cations. And the anions, the major anions, chloride, sulfate, bicarbonate, carbonate, and nitrate. So these are the most common, the most common. Evapotranspiration, this is an additional factor in causing salt-affected soils in these areas. Evapotranspiration, the loss of water through both evaporation and transpiration of the plant, through the plant. Evaporation directly and transpiration is by the plant. Drainage may be due to a high water table or to low salt permeability caused by sodicity of water. So, if you don't have good drainage so that the salt movement will keep on downward, you can have high water table or low soil permeability, and this can be caused by sodicity, by the sodium on the exchangeable. We will talk about it later. And the irrigation water quality. So these are all possible causes of salinity. Where do these salts and sodium come from? Now, how do we talk about salinity and sodicity? Sodicity, the problem of sodium. Sodic soils, sodicity, sodium problem, salinity, general salts, regardless of what they are. What are the parameters? What are the parameters we use to describe these types of soil? The parameters used to characterize salt-affected soils depend on concentration of salts in soil solution, amount of exchangeable sodium on the soil. So, how much salts we have in the soil solution, and how much exchangeable sodium on the soil exchange system. Exchangeable sodium is determined by exchanging sodium with another cation and measuring sodium in solution. How do we measure exchangeable sodium? You remember that anything that's on the exchange site, you cannot remove it with water. You have to remove it with another cation. So you have to bring in another cation that will take the place of sodium on the exchange, so sodium will come out to solution. So exchangeable sodium is determined by exchanging sodium, which is on the exchange sites, with another cation, and then we measure sodium in solution that comes out. The concentration of salts can be characterized by several indices. Indices, the plural of index, what are a measuring way of indicating how much we have, what are the different, again, they can be also called parameters, different indices that we can measure and talk about salinity using those indices. Total dissolved salts, and it's abbreviated TDS, total dissolved solids, TDS. We will talk about them also in more detail. Total concentration of soluble cations, total soluble cations. Total concentration of soluble anions, total soluble anions. And we have the electrical conductivity, EC. Okay, first let's talk about the total dissolved solid, TDS. How can we measure this? This can be measured by evaporating a known volume of water from the solid material to dryness and weighing the residue. So if you want to know how much you have salts and measure it in terms of total dissolved solids, you bring that from a salt solution or irrigation water, whatever type of water related in agriculture that you want to know how much salt in it in terms of TDS. You take a certain known volume, you put it in a beaker or in any container that takes heat where you can heat it, and you evaporate that. Of course, you know the volume you have, and you know the mass of that volumetric flask or beaker or whatever you are using. And then after it dries out, you weigh that again, so you know the mass that remained. And the mass came from a known volume. So it is a known amount from a known volume. TDS is a useful parameter to measure the osmotic potential. This is tau. This is how we refer to the osmotic potential. It gives us the capability of the plants to take water from the soil. The higher the osmotic potential, the more difficult for the plant to take their water from the soil. An index of the salt tolerance of crops. For irrigation waters with TDS from 5 to 1,000 milligram per liter. Remember, this is a known massive thing in a known volume. So we can, that's one unit, you can use that, but you can use all kinds of units as long as you have a mass per volume. Remember, we took a known volume and we evaporated it, and then we weighed how much residue was. So that's mass per volume. So in this case, we can say if the irrigation water with TDS 5 to 1,000 milligram per liter, tau, this is the one that we said the osmotic potential, we can approximate it from this number if we have this range. So tau, we put it negative because it's a negative pressure. It's the amount of how much it resists for the plants to take their water from the plant. That's why we have always a negative sign in front of it. Okay, so minus 5.6 times 10 to the minus times TDS in milligram per liter if it is in this range. These kind of relationships, they are not laws. They are not something 100% accurate. They are relationships they find statistically when they measure salinity in so many soils around the world, and they find relationships between them. So this what we call kind of simple primitive type of relationship, but they are not laws, but we can utilize them so that we get an idea. If it's hard for you to measure tau, you can, and you know TDS, so from this value you can approximate the value of tau. TDS can be estimated also from another salinity index, the EC, electrical conductivity. TDS equals 640 times EC. The EC values has to be, we will talk about them also a little later more. This is Siemen per meter. This is Siemen per meter for EC of 0.125. If the range of EC, whether if it's for irrigation water or of salt solution that you extracted from the soil, if the EC is in the range of 0.1 to 5, this is Siemen per meter, you can multiply that number you obtain by 640 and you obtain TDS. Now, if the EC is greater than 5, you multiply that number that you obtain, the EC you obtain, if it's greater than 5, multiply it by 800 to get the TDS. So they are different factors for different ranges. TSC, remember we talked about the cations, soluble cations, soluble and soluble anions. You can also approximate them from EC. If we want these numbers to be in moles per liter, you multiply by 0.1. If you want them in millimoles per liter, which is a smaller unit, of course, you multiply by 10. So again, these are approximate things. They are not laws, they are not rules 100%, but they are obtained from lots and lots of data from the field, and scientists get these approximations to help people when you cannot determine something and you have the access to determine another thing. From that, you can calculate the one that's difficult to obtain. Okay, electrical conductivity, or we abbreviate it as capital E, capital C. The preferred index, remember we talked about indices, different things, different numbers we measure to talk about salinity. So the preferred index, and the plural of it, remember, is indices. The preferred index to assess soil salinity is electrical conductivity. EC measurements are reliable, inexpensive to do, and quick. So why so many laboratories measure the salinity using the electrical conductivity? Because they're good, reliable. That means you get good indication of what salinity is. They are very inexpensive. The instruments that you use to measure electrical conductivity are not very expensive instruments in the laboratory, and they're quick, they're very fast. The EC is based on the concept that the electrical current carried by a salt solution under standard conditions increases as the salt concentration of the solution increases. So why do we, somebody might ask, how come we measure electricity, electrical conductivity, and we are talking about salts, the amount of salts? It's based on the concept that the electrical current carried by a salt solution under standard conditions increases as the salt concentration of the solution increases. When you increase the salt concentration of the solution in a solution, that means you are increasing the ions. And how is the electricity is transported, or how is it conducted within a salt solution? Through the ions. So the more salts, the more ions, the higher the current that will be carried out. So this is how the relationship between the electrical conductivity, the higher it is, that means the higher, the more salts you have, the more ions you have because of the higher amount of salt in solution. Electrical conductivity is expressed remember, we had this term before. Remember when we talked about cation exchange capacity, we say this term is used. How do we write it? What kind of units we use? How do we express it? This is the meaning of expression in this case. Electrical conductivity is expressed in micromoles per centimeter. These are the older units that scientists used to use. Micromoles per centimeter. Micromoles, MHO, centimeter minus 1 per centimeter, or in millimoles per centimeter, MMHO, millimole per centimeter. These are the old units. And actually, you remember Ohm's law. You remember you took that of the resistance in electricity. If you studied that in physics, if you take the opposite, Ohm, OHM, and Mo is the reverse of it. So that's why we talk about here conductivity, which is the reverse of the resistance. Ohm's law originally talked about the resistance of any medium for current, for the electrical current. So if you reverse it, OHM, ohm, and now we say Mohs to measure conductivity. In the SI system, the new system that most people use and most scientists use now, EC is measured in Siemens per meter, S per meter, or as this is Siemens per meter. To work with nicer units, the matter of using which subunit of the major unit, this is the original unit. Now we use this is Siemens so that we use simple units that we can deal with. And they chose this because this is equal to the same old one that people and scientists used to use. This is Siemens per meter equals 1 millimole per centimeter. So same millimole per centimeter, this is Siemens per meter, are the same in number. Okay, EC, electrical varies according to method used. We have many different electrical conductivity values. One of them is the ECE, is that of the extract of a saturated paste. I'm sure you will take saturated paste in another course, some other course. We cannot go through this. I'm sure you're familiar with it. And I have talked about it a little bit when I talked about salt solution, how do we represent salt solution? One of them is to make a paste and get the extract of that paste. So if you measure the electrical conductivity of that extract from the saturated paste, we call it ECE, the extract. ECP is if you measure the conductivity of the paste itself. You put the electrodes in the paste itself without getting the extract. So that is the ECP, the paste itself. ECW is the EC of a salt solution or water sample. So anything that's solution, aqueous sample, we put W. It can be salt solution or it can be water sample. ECA is the EC of a bulk field, so that's in the field. There are instruments, we'll talk about them very briefly. We'll not go in details about this, but it's good for you to know they exist. So you can measure the electrical conductivity of soil in place, in the field. So we call it A. ECW of the irrigation water. If you measure the ECW for irrigation water that you're gonna water your plants with, if this number is less than 0.7 Siemens per meter, that does not cause any problem to most plants, no problem. So you know that your irrigation water is good. If the ECW greater than 3 Siemens per meter, can affect the growth of many crops. A lot of crops start suffering, then you would have to watch it. You know that this irrigation water is not good. Okay, there are, again, we call these, remember, I told you about empirical or not very accurate, super accurate, but they give you some kind of relationship. They obtain them from statistical analysis from so many samples. They find relationships. So these are not rules. They are not by law, like this is a rule, but you can utilize them to approximate. So that's why we call them empirical relationships between ECW and ionic strength I, which corrects for ion pairs I equals 0.0127 ECW. I is difficult to measure. If you remember how you have to measure the concentration of all the cations, all the anions, you remember we already went through that in the chapter of salt solution. So if you want to approximate I from EC, you multiply by this number, 0.0127. So where ACW is again in decisiemens per meter, which is the standard unit that's used. There are rapid instrumental techniques for determining EC and computer-based mapping techniques. Remember, these are what I told you. You can measure the salinity in the field. This is good for monitoring. If they say they want to keep up with the salinity, they are doing some treatment, they are leaching salts, and you want to keep up with all these salts, what's happening? They put certain type of instruments in the field. Okay, so these types you put in the field and you can monitor, and they can connect them to computer. They can read the values from the laboratories. They have sophisticated systems. They've been using them in some of the advanced countries for a long time. Types of soil conductivity sensors that can measure bulk soil electrical conductivity. Always when you hear, remember we talked, if you remember when we talked about salt solution, the bulk salt solution, when you're away from the effect of the colloids and things, the major part of the salt solution, we call it the bulk salt solution, away from the effect of colloids, away from the effect of anything. And the same when we talk about the bulk soil, that means the general soil, not specific next to a very specific thing, the normal, how much you expect the average value of a soil. So they use different types, one of them called 4 electrode sensors. We have electromagnetic induction sensor, and we have sensor using time domain reflectometry technology. All these so that someday, if you ever heard of it, and maybe in some of your courses you might hear about some of these, and you might be familiar with some of them. Here I just mentioned them because this is not our purpose. I want you just to have an idea about the existence of these type of things. Okay, first we will concentrate on the Sodic hazard. What are the parameters we measure and we use to measure the Sodic hazard, the problem of sodium? There are several important parameters that are commonly used to assess or to evaluate the status of sodium in the soil solution, and on the exchanger phases. Remember, the problem mainly come from the exchangeable sodium, but also if you have lots of it on the exchange, there will be also some high amounts in the soil solution. The first of those parameters is what we call the sodium adsorption ratio, SAR, sodium adsorption ratio. Remember, you cannot use these abbreviations unless you mention the full thing, sodium adsorption ratio. Then you can put between parentheses capital S, capital A, capital R, but don't start with SAR and you expect people to know what are you talking about. No. After that, then if you're going to write an article or continue discussion or something, you can keep on talking about SAR after you defined it. And then we have the exchangeable sodium ratio. Remember, sodium adsorption ratio. Here, exchangeable sodium ratio, ESR. Okay, then we have the exchangeable sodium percentage, ESP, exchangeable sodium percentage. We'll talk about each one of them and define them one by one. First, let's talk about the SAR, sodium adsorption ratio. Sorry. I changed the by mistake. Sorry, I went to the next slide. So the SAR is commonly measured using the following equation. SAR equals sodium, the total concentration of sodium over calcium, concentration of calcium plus magnesium. You add them together and you take the square root of those to the half. Brackets indicate the total concentration of ions expressed in millimole per liter. The units are extremely important. If you change units here, this will not be valid equation. So SAR is defined as, that means the concentration, total concentration of sodium in the solution over the total calcium plus magnesium. Together, you take the square root of those. The brackets indicate the concentration of all of them in millimole per liter. So you can see that this is carried out in the soil solution or irrigation water. It does not have anything to do with the soil system itself. We don't mention about anything about exchangeable. So although it's an indication of how much sodium you have with respect to these two, it will reflect on how much will be on the exchange, but its calculation does not involve anything about the adsorbed sodium. We'll take the other two, ESR, exchangeable sodium ratio. Remember, it's extremely important to differentiate between this and the coming one. So here, Na soil, that means the exchangeable sodium. When we write Na soil, that means sodium on the soil system, on the exchange. That's exchangeable sodium over the cation exchange capacity minus sodium exchangeable sodium. So that means it's the ratio of exchangeable sodium to all the rest of the ions, the other cations. Sodium compared not to the total CEC, sodium ratio to all other cations. That's why we subtract sodium, exchangeable sodium from CEC. So that gives us the remaining of all the exchangeable cations. That's why we call it exchangeable sodium ratio, the ratio of sodium to the rest of the other cations, where the concentration of the ions on the exchange phases and CEC are expressed in mole charge per kilogram. Remember, whenever we talked about exchangeable, if you remember when we talked about that in the cation exchange part, we always said moles of charge for charge per kilogram. Just like, remember the CEC, we said centimole of charge per kilogram. Here we use moles of charge per kilogram. The US Salinity Lab reported a linear regression equation between ESR and SAR. The United States Salinity Laboratory, this is a laboratory, which means it's not a small lab. It's a big organization, but this is what it's called, the United States Salinity Laboratory. It's in California in the United States. And this is specialized in the study of salinity, and they studied soils from throughout the world. They are the most probably famous and known organization that studies salinity of soils in the world. It's called the United States Salinity Laboratory. So that's why they collect samples from all over the world. They are the ones who find relationships. So if you want to know the relation between ESR, this is harder to measure because you have to measure exchangeable sodium, which is not easy. You have to exchange it with other cations and get it in solution and measure it. So if you want to estimate the exchangeable sodium ratio from SAR, which is easier to measure, you have this type of relationship. Don't memorize these type of relationship, but if you ever needed them, they are in your textbook, they are in the literature, you can go back and find them, but don't memorize them. If somebody wants you to find one from the other, they should provide you with this equation or empirical equation. And then the last one we have ESP, exchangeable sodium percentage. Now this is exchangeable sodium over the total CEC. So what is the percentage of sodium from all the cations, including sodium? Remember this one, we subtracted sodium from CEC. So it's the ratio of sodium to others. Here, it's the percentage of sodium in the CEC. how much of the CEC is sodium. So you say the exchangeable sodium over CEC times 100 to get you the exchangeable sodium percentage. Soils with an ESP greater than 10 are very impermeable, which seriously affects plant growth. This you should, I'm hoping that in your soil physics or some other courses, they will explain to you more why sodium makes the soil so dispersed and impermeable, and I hope you have that kind of information. So we finished our lecture. There will be another lecture